Welcome to the Socio-Environmental Modeling case study by James Knighton, Kelly Hondula, and Margaret Palmer. This video provides examples of the use of socio-hydrological modeling to understand the difficult problems associated with flooding. Drawing on two papers that use different approaches to explore social dimensions associated with flooding risk and losses, this video covers four related topics. First, you'll hear about using a generalized, process-based modeling for simulating community responses to infrequent disasters. Second, we'll discuss the use of a machine learning modeling approach to relate disaster and loss to socio-economic conditions. Next, we'll discuss very briefly what significant amounts of data are needed for both of these modeling approaches. And finally, we will come back to the two approaches to compare them and the types of research and planning they support. Before getting to the models, let me provide a little background. First, the number of people living in flood-prone areas is growing very fast. People move to these areas typically because housing is cheaper, even though it is hazardous, and climate change is leading to increased flood frequency and/or magnitude. It turns out that if you look at the insurance records associated with floods, you'll see that the economic impact of floods in the US alone rose from $1.1 billion in the 1980s to $4.92 billion in the 2010s. Globally, World Resources Institute projects losses due to river flooding will rise from the current level of $45 billion to $535 billion by 2050. In parallel with these increases, we've actually seen that governments in the US and abroad are paying more attention to the problem of flooding. So why is it we can't seem to reduce the risks to people? Well, first, consider the fact that risk is not as simple as it sounds. The risk posed by flooding is actually a complex interaction between at least three things. 1. Hydrological hazards, such as rivers flowing over their banks during periods of heavy rainfall. 2. Our exposure to these hazards, such as living in floodplains. And 3. Our shifting vulnerability to these hazards, such as our capacity to rebuild or relocate after a flood. It may not surprise you to hear that most of the attention has been placed on number 1, hazards. There are continuing efforts to quantify and reduce it by, for example, providing better floodplain maps or producing better models of river flows. But there is some evidence that these efforts might actually drive counterintuitive behaviors within communities that actually increase exposure and vulnerability, namely the other two dimensions of risk. All aspects of human behavior are inherently unpredictable and constantly changing. But at an aggregated level, collections of people who are individually unpredictable often display fairly predictable patterns as a group. In a specific problem context, patterns, including those associated with human behaviors and risk, can be captured and used to inform model structures. One way to deal with this comes from pattern-oriented modeling, an approach ecologists have used for years. And modelers like Volker Grimm argue it is a useful approach for socio-environmental modeling of topics like those we are focused on here. Before we turn to our process-based modeling example, let's review just a few of the other things we know from human behavior research that inform flood risk modeling, especially those that influence vulnerability. For example, we know that in general, having experienced a flood in the past changes how people value insurance, but it's really hard to predict how much this matters for a given individual. There are lots of reasons why people don't have flood insurance policies, but we know from looking at flood policy records and population densities in floodplains that immediately after major flood events, the number of policies tends to increase while populations decrease. Floods vary in their magnitude and also vary in frequency, so those decreases in population density in the floodplain may decrease more if floods are large, and floodplain communities have experienced a number of them. But if a community hasn't experienced any floods for a while, populations increase and the number of policies tend to decrease. So we use knowledge of these empirical patterns to develop equations predicting responses to external perturbations and what happens in the extended periods between disasters. When someone has experienced loss personally, we assume they are most aware of dangers immediately after the loss. In other words, awareness goes up. If they did not experience loss directly, but know someone else who did, say, a friend, their awareness will increase, but not as much as with their own experience. Reading about a disaster in a foreign country might not have any discernible effect. Flood risk is not a salient issue to them, so they are inattentive to the potential for floods. This can be the case even if actual risk is high. In the absence of any exposure to danger, people likely move on and become engaged in something else. Humans tend to prioritize a small set of issues. Environmental disasters are likely to receive little attention if individuals, policymakers, and political leaders become engaged in more pressing problems. Those with less power to influence attention are also those poorer or marginalized communities that suffer the most from floods. For those, what others may view simply as nuisance flooding may actually be devastating because they do not have the resources to rebuild. Certainly, individuals or communities vary considerably in their tolerance to risk. Coastal communities where properties are second homes to wealthy people may be more tolerant of possible damages, as they might not pose an immediate threat to the housing status of the residents. Risk-averse communities encode risk preferences in infrastructure or flood policies that can help to limit the impact of memory loss on future flooding vulnerability. So, information like this on types of decisions communities make and what influences those decisions can all inform flood modeling. Okay, let's focus on models. First, we'll illustrate a process-based modeling approach. These models are based on an understanding of the relevant processes and their general dynamics. That is, they are built on explicit assumptions about how the system works and are fairly easy to interpret compared to the detailed simulation models. A set of mathematical equations is used to describe those processes which represent our general understanding. An advantage of them is that the same model can often be applied in multiple settings, and they are easily understandable. In fact, if they are very simple, the set of equations can be solved analytically, for example, just using algebra or calculus. The model we'll discuss was initially proposed by Barendrecht et al. 2019, which is a simplification of several previously published models. This model suggests communities can be modeled with several simplistic relationships. First, the economic damage of a flood is related to both the magnitude of the flood and the salience, or relevance of flooding risk within a community. Second, community migration or emigration rates are in some way related to risk salience. And third, as indicated earlier graphically, community awareness of risk increases immediately following floods, and without floods, risk gradually increases as community precautionary measures slowly degrade. In other words, the salience of floods has declined. Recall that we mentioned earlier that risk can be broken down into three parts: hazards, exposure, and vulnerability. Now see examples of the factors that each of these three could involve. In this case, we are primarily focused on the role of behavior, so for modeling purposes, we set the hazards and the aspects of exposure as fixed. You could think of them as external to the system dynamics we are going to model. This simplifies our modeling. Recognize that factors influencing vulnerability work in concert with river flows to influence risk, and risk is operationalized in the model based on economic damages which we call losses. The effectiveness of the preparedness can vary, and risk is associated with river discharge when it exceeds a certain level. Here's the general equation used to model these potential losses, which for simplicity we are calling risk. Note that all of the model processes are controlled by a suite of calibration parameters that determine the shape and strength of these responses. So, for example, the relationship between river discharge and losses can be varied with the beta parameter, while the effectiveness of preparedness can be changed via the alpha parameter. The relative risk that this model calculates is then rescaled to a loss, L, by multiplying by population density, D. That loss in a year can induce an increase in awareness, A, and the anxiousness parameter, alpha A, defines the extent to which past flooding will induce an increase in A. Years without loss cause A to decrease based on forgetfulness, mu A, the ambient lapse rate. So awareness is very much a function of people's past experiences and their memory of those, which we illustrated a little earlier. The changes in awareness in turn drive changes in population density, here labeled D. Changes in awareness also influence preparedness, and so forth. I'm sure you're getting the gist now of how the equations are linked and how together their dynamics determine the outcome or losses. Now, Recall that all of the processes are controlled by the parameters that are calibrated using data. In our case, the calibration dataset is from records of high streamflow events, flood insurance policy uptake, and claims submitted after floods. I'll discuss that dataset more later since it's also used for the machine learning modeling approach. In theory, we could look at actual damages from historical floods and estimate these parameters. However, if we do this, we're making simplifying assumptions, namely that other parameters remain the same. For example, say we use flood data to estimate the forgetfulness parameter. If so, we're assuming migration is primarily related to flooding, but we know that people move around for many reasons. Also, because we don't have a lot of data for calibration, we must assume that parameters are time invariant, meaning community behaviors like willingness to take risks do not shift across years. On the surface, this is concerning, as we know that risk behavior changes over time, as do all the thoughts and perceptions of individuals. Third, for model calibration, which we will discuss later, we use records of flooding, and we must assume these records actually reflect mechanisms in the model. For example, the risk-taking attitude parameter that determines the strength of the relationship between awareness or salience and preparedness might more accurately reflect barriers to taking precautionary measures and not an actual tolerance for risk. Such concerns are valid and not easily addressed. And although process-based modeling allows for testing what could happen under a wide range of possible scenarios, we must accept the built-in assumptions as valid. So now we've provided a brief description of process-based models. But what if we decide the overall problem is really too difficult to be treated with a small set of differential equations? After all, patterns that emerge at the community level are influenced by a myriad of external drivers, such as advertisements, political affiliation, economic and racial divisions, complex histories of policy, etc. If we fully understood how socio-environmental processes worked in a fully mechanistic way, it would likely be challenging to collect sufficient data on each independent process in order to calibrate such a model. For these reasons, a less structured approach to modeling flood risk behaviors may be more appealing. Now let's turn our attention to machine learning models. These provide a parallel framework to process-based models. They benefit from having less rigid structures or assumptions about the relationships between inputs and outputs. Machine learning models are created by running procedures, called algorithms, on data. Algorithms use pattern recognition processes to learn from the data to improve our ability to make predictions. They are more efficient at identifying less intuitive relationships between variables of input data and may therefore be more appropriate. With machine learning, if we wanted to predict areas where flood insurance claims come from, we don't need to develop a whole conceptual model about how the underlying processes work. Instead of having to specify which variables are related to which and how, we just supply data about all of the variables that we think are relevant for explaining the metric we're interested in predicting. In this case, variables like these should be useful in predicting the rate at which flood insurance claims are submitted. Historical data, or a subset of all existing data that are available for each of those variables, are input into ML algorithms and a predictive model is identified. It could be something like a complex regression or network model. The input data are called the training data. After separate data are used to test the model, current data or different data can be input and the metric of interest predicted using the model. The two primary downsides of ML for socio-environmental modeling are they require large data sets. And second, machine learning algorithms are not easily interpreted. Predictive relationships are developed, but it may not be clear what social or environmental processes are driving those. So, while they might predict community behaviors well, it is not straightforward how the black box of a machine learning model can teach us about the mechanisms occurring within communities, and therefore our conclusions might require tempering. Actually, both approaches, the process-based approach and machine learning, rely on having datasets for calibrating parameters or for fitting statistical relationships. In the past, researchers working in this area have primarily worked with either synthetic datasets or historical records from small, geographically confined areas. Now, the culture around data sharing has shifted, meaning we have an increasing amount of publicly available data from governments and researchers to help drive socio-environmental research. For example, in 2019, FEMA released the Open FEMA database containing historical flooding claims and policies for the entire U.S. This dataset includes over 2 million records of flood insurance claims dating back to 1978, pinpointed to census tracts. Datasets like these spur new hypotheses and models and help researchers tackle the next generation of challenges that more explicitly consider the human dimensions of risk analysis and SE research more broadly. Our research has used this Open FEMA dataset in combination with streamflow records from the USGS, demographic data from the US Census Bureau, and other open data to study flood risk in the US with both of the modeling approaches we introduced earlier. To understand how to make use of the data, we need to know some background about how the National Flood Insurance Program works and what is represented by a record in this dataset. The NFIP is a government program that makes flooding insurance affordable to people in the U.S. who live in floodplains. The NFIP was designed assuming it was a revenue-neutral program around the belief that after a major flood event, an individual would want to relocate. A one-time insurance payout would help that relocation, gradually reducing floodplains populations, and eventually the need for NFIP. However, as we mentioned earlier, flood damages are still increasing, and the total claims submitted each decade continue to rise. This means that the program has not worked as assumed. Rather than remaining revenue neutral, the program has been bailed out twice by Congress. Parallel U.S. federal programs such as USACE flood control projects and federal home buyouts still exist, and yet some residents live at risk without insurance. It's not immediately clear why. The NFIP data helps answer this question by allowing us to quantify where and when losses occur, the amount of damage, and also the proportion of the population that has active flood insurance policies in a given year. If either of our models are able to recreate patterns in the real-world dataset, it means we may understand the current system well enough to identify why it's failing. Okay, let's return to the two modeling approaches we talked about and compare them. Where do they agree? Both models showed skill in predicting the insurance market, but they did this through different means. First, in terms of agreement, both modeling case studies demonstrated two broad drivers of flood insurance: hydrology and social demographics. Hydrology makes sense. Those properties most exposed to flooding are most likely to have and submit insurance claims. Both studies indicated that certain demographics, race, poverty, political affiliation, and housing status played some role in flood insurance claims. While they both identified these two drivers, they did so through different means. The process-based model considered flood insurance records in a time series of peak streamflow. It took into account how communities might change over time in response to past experiences. While it didn't know anything about the demographic data, a post-model validation correlation analysis showed relationships between model parameters and demographics. In contrast, the ML model required many different types of data points on each city, and it did not allow for dynamic feedbacks that changed community response. Rather, this model was a sophisticated regression, predicting aggregated flood claims based on hydrologic characteristics and demographics. The ML model, while powerful, is limited in its application. We can say which demographics are related to flooding, but the model offers no additional clues that would allow new hypotheses. That is, it is difficult to interpret or generalize from. The process-based model attempts to describe flooding as a function of those different assumptions made about how a community's collective preferences, perspectives, and actions are related. The calibrated parameter values indicated that the insurance markets may be driven by memory in some locations and a risk-enduring situation in others. For example, our analysis showed that clusters of metropolitan areas were well described by a similar set of model parameters, suggesting the process-based model was identifying regions with similar behaviors. On the other hand, machine learning models are highly tuned to training datasets and therefore not appropriate for extrapolation. In contrast, the process model offers us a chance at predicting future conditions. Because we have a process-based understanding of insurance dynamics, we could possibly use this model to study community response to new external forces, such as altered streamflow regimes under climate change. These are just two approaches for studying flood risk through socio-hydrologic modeling, making use of large publicly available datasets. Both studies highlight the connections between the social and environmental realm, Understanding flood damages requires considering not only hydrology, but also the social factors that lead to people being in harm's way and how they respond to flood events. That brings us to the end of this socio-hydrology modeling case study. Thank you for watching.